Okay, hi everyone, can you hear me? You should be able to. Yes, okay, thanks. All right. Okay, also, sometimes this crashes a bit, so please let me know if like I stop writing, for example. Okay, good. All right, so thanks for accommodating this. I know it's annoying to have lectures only online, but it was actually at a good time that we made this decision. So for example, we got a message from childcare this week saying that there were 4 cases just in the weekend among kids in the same kita as mine. I heard that a colleague of mine just got COVID from teaching in Vienna. And overall the risks do not overcome the benefits. And especially because the lecture is not just a lecture, it's also the public transport, and you're having to have lunch around there in the very overcrowded menses and so on. So we've decided to move everything online. Okay, so please continue to ask questions, especially if you see typos or if you don't understand something or if some explanation seems a bit dodgy, because this is what makes the lecture good. Okay, so we'll continue today into this generalized spin, and we'll talk a bit, we continue to characterize this space, and then we'll talk about what happens when you take 2 spins together, like for example, 2 electrons together, and we'll see what happens in this case. Yeah? So this is a bit of like when I go traveling with my kid and I have to tell him, look, when we arrive, it's going to be really cool. So you hang out with me for this 5 hours of driving. And so the solution is cool. It has lots of applications. So you just trust me on this, and we'll see how it goes. So in a world, meaning a Hilbert space H, where there exist some operators, we know nothing about these operators, right? Except that we know their commutation relations. So we just started by saying, well, we have 2 we have these 3 operators. We don't know anything about them. We don't know anything about the Hilbert space. The only thing we know is that they satisfy these commutation relations. We can even postulate this. And then we are going to go and explore what kind of space this is, right? And this is, again, like science fiction, like saying in a world where humans can teleport or can do some magic, or we colonize Mars and the asteroid belt, what should be the social implications of this? It's exactly the same thing. So what did we do? So we defined these operators as square and up. And the ladder operators, so this is xx squared plus squared plus z squared. And we did this plus and minus ladder operators, which are just the sum of x and y. And what did we find here? What did we find out about these new characters in our story? We found that, well, we don't even need to write such that because this is a consequence. Okay, so what did we find? It turns out that S squared commuted with all the other, with S, X, Y, and Z. And as Z commutator with S plus was what? It was plus H bar S plus. And with S minus, it was minus H plus S minus. Yeah. And we also saw that this will be useful later when you take the transpose conjugate of the S plus you get the S minus, and vice versa. Right. And then what else did we see? Well, we saw that here. If we looked at the SZ eigenstates, and we just call them M alpha, just to say that there's something in them, there's some characteristic in them that gives us the eigenvalue, that's the M. And there's some characteristic alpha that does not influence SZ, right? Maybe it influences the other spin operators, maybe some other operators in the Hilbert space, we don't know. Right, so this is a number. And we don't know anything about M yet. So what we found was some subspaces, and don't worry for now about the actual definition of what a subspace is. We will define this next time. We'll also define what this direct sum is next time. But for now, you can just think that the big Hilbert space is made out of Hilbert spaces with different S values, where this HS are the eigenspaces of the S square operators, right? So this is Tuk. So suppose, for example, that for trying to look for a more relatable analogy. So suppose that we want to characterize the dialects in Switzerland, okay? And the first thing we do is to say, well, Switzerland is split into 4 languages, right? You have German, Italian, Romance, and French. Okay, and the analogy is that those correspond to these different values of S. Okay? So this number here is just the eigenvalue of S squared, and we decide to write it in this form because it will turn out to be useful to write it in this form. Yeah? So this corresponds to the big languages, and then inside each language there's many dialects. So there's many values for M. Okay, so let's keep this in mind. Good. And one thing I kind of told you, but we didn't prove, so we'll prove it now, is that inside each of the subspace, if we act with this operator or with the ladder operators or with the X, SX or XY, we never leave these subspaces. That's why what makes them relevant. So let me just make this precise. So if we have some psi that belongs to HS, then if we apply any linear combination of this, so J is X, Y, Z, to the state, we are still inside the same subspace. Okay, we'll prove it in a just so this includes, for example, S plus because it's SX plus I SY, right? So this is included there. Okay, so now let's just prove this. How do we prove that it's still in the same subspace? Well, we need to prove that it has the same eigenvalue for S squared, right? This was the definition of this subspace. Okay. So this is the same as saying, look, if you take a Swiss dialect and you change the vowels a little bit, or you change the way consonants are pronounced from sh to you still don't change language, right? You're still in the Swiss German. You don't suddenly move to French. Okay. So that's the idea. So how do we prove this? Well, we just go see what happens when we apply S squared to this new state. And the idea is because S squared can commute with all the SJs with X, Y, or Z, then it can go inside here. So then we have sum over J, alpha J, Sj, S squared, juk. Right? And now this, I mean, because by assumption it was it was inside S, then we know that it corresponds to eigenstate, to eigenvalue S plus 1. So this is now, sorry, your lambda S, right, which we defined here, lambda S, right? This is the definition of the space. And then the same thing again, sum over J, alpha J, Sj, chuk, which is our original state, right? And this lambda S, remember, it's h bar square S plus 1. Let me just check that I had the h bar square there. Yes, I did. Okay. Right, so it checks out. So even if we apply these operators plus and minus, we're still inside the same space. Okay? Still inside the same language. Okay. And what else did we find? We found also that this S plus and S minus act as ladders, in the sense that we saw that when we apply S plus to some eigenstate of Sz, you got some normalization constant times n plus 1. And here's some alpha prime, because it could have affected the alpha prime, and S minus. You got a different normalization constant, which can depend on S and M. But we saw that we go up and down the ladder, right? This could be a different state. Okay, good. So this means that we have what? Somehow for a fixed HS, we can have different values of M. For each value of M, we can have different values of, well, maybe I write here the alphas. Okay, and we don't know much about this, except the only thing we know for now is that with S plus, we move up, and with S minus, we move down. Okay, that's the only thing we know. Okay, so now we're going to learn more about this HS space. Okay, so we need some building blocks that we'll use many times. And the first one is to look at this operator, S minus S plus, and we'll see an application right away. So let's just write what this is. So we have here Sx minus I Sy, and then we have Sx plus I Sy. Okay, so now we have 4 terms. So we have Sx, Sx, so it's square. We'll have this term with this, will give us plus Sy squared. And then we have what? I times this and this minus this and this. So this is Sx Sy minus Sy Sx. But this is just a commutation of x and y, and we know what this is, right? So this is Sx Sy, which is I h bar Sz. And this thing we can rewrite as being just your S squared minus the term that's missing there, which is ZZ squared. Yeah. And this will be useful. Why? Because now we can write the whole thing as S squared minus SZ, oh, sorry, minus SZ. And then what's left here is 1 SZ from there, sorry, from there, and then from here the H bar. So plus H bar. Okay. So you can check at home that this is true. And this is just a neater way to write this that will be useful, because now we will need the second building block, which is what happens when we apply this to a stage. So if you have S minus S plus, and now we apply to some stage eigenvector of Sz. Yeah. So then what we do here, well, is to replace with what we just found. So this is the same as S squared minus SZ H bar plus SZ applied on M alpha, right? So now S squared apart on M alpha, because this lives inside one of these HS subspaces, this is going to be your lambda S times the same state again, minus, well, let's just do here first one. When we apply here the SZ to this, we get H bar times M, M alpha. And now the only thing left to do is to apply this one. So this is a number, I can move it to the back. And now we apply this SZ here, and we get again H bar M, right? So then we get S minus H bar M, H bar plus H bar M. Let's just replace what was this lambda S. So this was H bar squared. S plus 1 okay. Minus, and now here we have again H bar square, and then we have M plus 1. Okay, remember this whole thing, this is just a number. It's just a number that depends on M and on S. Okay, this whole thing. Okay, good. And you can do as homework, maybe you'll do it in the tutorial, what happens when you do it the other way around. It's very symmetric, you just get a minus sign at some point. So you can do it now if you want, or we can do it here. So these are just technical ingredients that we're going to use. So now we want to bound this space vertically, okay? So we want to know what are the maximum and minimum values for M. And so the trick we use, so is the following. Well, let's take some state, which is S plus. Okay. This state may not be normalized, but you know, it's still a state. So if you do within a project of the state with itself, it must be a positive number, right? Worst case, it could be 0, but it can never be negative. That's just a property of the Hilbert space. Okay. So then just replace here. So this is what? So this is M alpha. Oh, sorry, this. Let me just make sure that I put the plus down there. So S plus dagger, S plus M alpha, right? But S plus dagger, we know what this is. From the beginning, this is just S minus, S plus. Okay, and now we have this thing here, which we just computed before what it is. Right, this is exactly what we did before here. Oof. So let's just write it. So that's going to be a number, which is H bar squared, and then this whole thing, S plus 1 minus M plus 1. And then we still have here these two states. But this is the same state, and those are normalized by assumption. So this is just 1. So then we're left with what? 0 is smaller than this thing here. And H bar is a positive constant, so we can get rid of it. So then we have that S s plus 1 minus m plus 1 must be a positive number. And the only way for this whole thing to be positive is if this is larger than that. And the only way for this to be larger than this is if s is larger than m. So then you can do the whole calculation by hand if you want, but the conclusion is that s must be larger than m. Okay. And now this was one direction, and the other direction is by taking, you can do at home, by taking a new state, which is now s minus applied to this. Then you do the whole thing again, and then you get that s must be larger than minus m. So what does this leave us with? It leaves us at s is fixed, right? So the only possible values for m are between minus s and s. Okay. But how can this be? I mean, we saw before that, this is very ugly, sorry. We saw before that, well, where are we? Yes, whenever we apply this operator, this ladder operator, we go up, right? So what is stopping us from going up indefinitely, right? Also, we don't know, I mean, I wrote here m as discrete states, but in principle, it could be a continuous, right? So we don't know that we're not allowed to just go up indefinitely. So how does it come about that m has a top and a ceiling? So it would have a top here at plus s and a ceiling here at minus s. Okay? So how can this be? We will do this. We'll do this in 2 steps. So the lecture notes should be online now, and I'm just changing the order slightly from what we're doing for how we're going to prove it, because I found this a bit more convincing this way. So what we'll do is to first, we'll find these coefficients. K and K prime, these normalization coefficients. And then from here, we'll find expression for s plus and s minus. And from here, we'll see, yeah. From here, we'll see how this can be. Okay, good. So what's the starting point? Is that when I have s plus applied on m, I'll get some constant times m plus 1. So we're going to find this constant. How do we find it? Well, we know that the final state is normalized. So 1 is m plus 1, m plus 1. And for now, I'm forgetting about the alpha, okay? So let's just say that m is m alpha, and m plus 1 is m plus 1 alpha prime. I just don't want to write the alphas and alpha primes all the time. So, okay, so this is 1. And now I just use the expression above to say, well, this is then 1 over k squared. And now right, I just take this and the complex conjugate, which we know now it's s minus, s plus. Now this we know because we just did it before. So this is 1 over k squared. And your square s plus 1 minus m plus 1. Took. And then we have again m which is 1. So from here follows that k is the square root of that, and let's just keep everything real numbers. And plus 1. Okay, good. So what does this tell us? So first we know that S plus applied on the state M is H bar. And now this thing, S plus 1 minus M plus 1. Okay. So in particular, what happens when we apply S plus on the top state? So on M equals S. Well, then we get that here H bar, and then S plus 1 minus S minus 1. And here would come this state that doesn't exist, which would be, but this state doesn't exist because it doesn't matter, this whole coefficient is 0. Right. So then this whole thing evaluates to 0. Similarly, you find that S minus M is, surprising no one, S plus 1 minus, and here M minus 1. And if you apply S minus to M equals minus S, then you get 0. Meaning what? So let's draw again this this diagram, or we have here the possible values of M. There's still possible values of alpha that we don't know about. And what's happening is that it has some ceiling S here, some bottom minus S there, and I don't know if you can hear my computer. It seems like it's about to. A second, just pull some things because I'm getting really hot. All right. So we know that with the S plus, we go up in some way, but if we hit any of these tops, any of these top states, then it gives us 0. And with the S minus, we go down, but if we hit any of these bottom states, we get 0, okay? And then you ask, okay, so what if we started, let me just copy this. What if we started in some value, I don't know, here, for example, so S minus 0.8, right? Then if we apply this coefficient, this S plus operator, and we could compute what number would go here, and this would not be 0, right? So then we wind up with the state up here. But this state is not allowed because we saw that that M is bounded. So the only way to forbid this from happening is to say, well, this state, this red state here, down here, cannot exist in the first place. Because if we start from any state that is at a fraction of an integer away from S or minus S, then we can always go in these things. We can always add +1, +1, and you end up in the forbidden zone. Does that make sense? So then the conclusion is that M cannot take continuous values. So M can only belong in this set minus s plus 1, chuka chuka chuka, s minus 1, s. Again, because if it was anything in between, then you could apply this these ladder operators and get in the forbidden regions. So here you can't have any state, and here you cannot have any state. Okay, so this is how we quantize spin, right? We started by saying, well, look, it could even be a continuous Hilbert space, but it turns out that the eigenvalues of Z are discrete. And this is how we did it. Okay. Good, so now let's try to find out a bit more about this. So we need to have an integer number of steps to go from the bottom to the top, which means that then, the top minus the bottom must be a natural number. So 2s must be a natural number, which means that s, the possible values for s are like 0, the triple case, 1/2, 1, 3/2, 2, 5/2, and so on. So the spin s can only have half integer values. So let me just give you some examples, because turns out particles have very different properties depending on the value of s. And s is called total spin. Well, it's called the spin number. We'll see later when we talk about angular momentum that there's some quantities that we call the quantum numbers, and this is one of them. S. So if s is 1/2, then what are the possible values of m? This is minus 1/2 or plus 1/2. Right? If s is 3/2, then m is, well, it can go for minus 3/2. Then we add 1, so we get minus 1/2. We add 1, and we add 1, and that's it. Let me do down here. If s is 1, what are the possible values of m? So this is belongs. The possible values of m are, well, minus 1, 0, or 1. So now it's an odd number. If s is 0, that's very easy, and there's only one. Okay. Now in particle physics, we call particles that have a half integer spin, we call them fermions. So for example, so this is when s is a half integer. For example, electrons, we saw, but also protons, and so on. So most things that matter is made of are fermions. So this all have spin 1/2 in this case. If they have spin 1, we call them bosons. So this is when s is an integer. And this turns out to be things like photons, something called gluons. In general, things that mediate forces, the famous Higgs boson, and so on. So for example, photons as have spin 1, the Higgs boson has spin 0. And if you go like to the Wikipedia page of the Higgs boson, you see that most of its properties are all 0, which just makes it so hard to find. That's why it took so long to come up with an experiment that is sensitive enough that can measure it. So we cannot just throw a Higgs boson through the Stern-Gala experiment, right? Because no, it cannot have different values of m, it has one value of m. Okay, so we bounded the space vertically, And now what's left to do is kind of bound it horizontally. So what possible values of alpha do we have for each m? I'm not erasing the board, so if you have questions, now would be a good time. Sorry, horizontally. Okay. So the idea here is to say that for every value of m, you have to have the same number of orthogonal states. So if we take, so let's see, idea for each m with same number of states of the form m alpha, where we can vary the alpha that are orthogonal. Okay, so we'll prove this going up and then we'll prove it going down. So so suppose that m alpha and m beta are orthogonal. And we're going to see that when they go up, they still must be orthogonal. So there must be space for in the subspace of m equals 1 to at least as many orthogonal states as here. So I'll just show it. So S plus m alpha and S plus m beta are still orthogonal. How do we show this? Well, m alpha minus, we just bring in the states and beta. Remember that this is the S plus transpose conjugate. Well, in this we know what this is, right? So this is that thing is that big number. So h bar squared s plus 1 minus m plus 1. And now we're left with m alpha and then beta, right? But these were orthogonal, so this is 0, so the whole thing is 0. So what this means is that when we go up, when we apply the S plus, it maps orthogonal states to orthogonal states, right? So you must have at least up here as many states as you had in the level below, because otherwise there's no space. So we cannot have this kind of situation where that operator maps orthogonal states to non-orthogonal states, right? I mean, this is true in general if you take quantum information theory, you see that this is true of quantum operators in general. Well, that's not true. It's true of unitary operators in general. Okay. So this means that the dimension of the subspace m plus 1 must be at least as large as the dimension of the subspace M. And now you can imagine that we'll do the same thing going down. So, and this is homework. So let me say this was part A and part B. So you can do exactly the same to just show that when you apply the S minus operator, these are still orthogonal. So from here, one concludes the opposite, so that the dimension of the space M minus 1 must be larger than the dimension of the space M. I mean, this is for M larger than minus S. Of course, when we get to minus S, then we go to the bottom. So this is for all M smaller than S. But what this tells us, so if the dimension of the next space of the next value of M must be larger and smaller, then it must be the same, right? So conclusion. Dim M equals dim M prime for all M prime. Okay? So this means that what we have, the situation we have is more like a rectangle. So you can have different values of alpha, but they must be always the same. Yeah, that's good. And here would be, for example, this would be what? Plus S minus S, right? So this is spin 2, for example. So it looks like this, which means what? It means I can take the space HS and kind of split it. This symbol means that there's an isomorphism, there's a one-to-one well-behaved function. Don't worry too much about it for now, which is the part that matches in the spin. So this would be the vertical direction here. Tensor, some extra stuff, which is what defines this alpha. Meaning what? That I can rewrite the states M alpha as, again, think of it as equality for now. M, this is what we care about, and then some alpha. So this is in the extra, and this is in the M subspace. What's the dimension of this? The dimension of H Z. Well, that's the number of possible values of M. So they go from minus M to plus M. That's so from minus S to plus S. So if you work it out, that's S plus 1. And the dimension of this, we don't know. But it's what we were calling before this dim M, right? It's this thing here that we... Okay, so now this is quite good because we started with very little, just this correlation, just this commutation relations, and now we kind of characterize the whole space, right? So we see, oh, it's a rectangle. It can only take discrete values in this direction. In the alpha direction, can take anything, but we don't care because we can factor it out. Right? It doesn't matter. We know that when we apply our operators, our ladder operators, we stay within column, so to say. Okay, and we know how to bound it with plus S and minus S. Everything is very well behaved. So just one more thing we can do now is to write the explicit form of this S plus and S minus operators, because this will be useful later. And then I let you go to the break. So S plus operators. So what do they do? Maybe it's easier to write it like this. When we apply it to M, it gives H bar S plus 1 minus M plus 1 M plus 1. So one can write the operator if you know how it acts on the whole basis, right? To know how it acts in all these M's. And this is the initial state, this is the final state. So we can write this matrix S plus as the sum over all M, go from minus S to plus S of, so final state, it takes this initial state M, and it's going to return this final state M plus 1 times some coefficient. So now to make things work out, we need to put here this the coefficient in the denominator. So S plus 1 minus M 1. And now note that when M turns out to be the maximum M, then this will, sorry, the other way around. Then this whole thing is going to be 0, not the denominator, but it goes here. Okay. Yes. Yes, so when M equals S, then these two terms are the same, so this whole thing is 0. So we don't have to worry about this M plus 1. It doesn't exist. So in matrix terms, well, let me just do the other one. So S minus is again the sum of M minus S to M plus S of H bar. And now we get here, same thing, except here M minus 1. And here M minus 1. So this is the final state and this is the initial state. In matrix form, and I hope I'm getting this right. So the diagonal is all zeros. And then I think the S plus has these coefficients here, just below the diagonal. So we go up. No, sorry. Let me think. Yeah. It goes here, sorry. It has all the coefficients here on top. So the lecture notes have it the other way around. And this one will have all of them here. And the size of this matrix is just given by S plus 1. Okay, good. So now we take 10-minute break and we can restart at 11 past. And then we'll see what happens when we start adding different spins. So when we take now 2 electrons, see what happens. So let's take 10 minutes and I'm here if you have questions. I'll just go grab some water and I'll be right back. Okay, let's restart. I just forgot to say something, is that we saw that this HS, we could split it into some, the spin version, the spin part, and the extra part. And when this extra part is trivial, so when this has dimension 1, then we call it a simple spin system. And in general, if you have some Hilbert space age with all this as where we can find these operators satisfying the commutation relations. So this, etc. The other two, we call this a spin system. And then in particular, if this extra part with the alphas is trivial, then we call it a simple spin system. Okay, so on Thursday, we'll have some exercise about spin systems, but now let's see what happens when we take two of them. So I take two electrons, they are both spin 1/2, for example, and I bring them together. What do I have? Okay, so the claim, the general claim, is that if I take a bunch of this SJs, okay, and I do the product, the tensor product of them, then this is still a spin system. How do we prove this? So we will see. We will prove it for two systems only. Okay, the general proof is exactly the same. And then we will analyze in more detail the simplest case where we just have like two electrons, two spin 1/2. So proof for H global is some H. So you have some spin 1 here, so some value, some fixed value of S, and then you bring another particle that has a different value of S. Okay. So this could be, for example, an electron and the photon, they have different values of S, so it's 1/2 and 1. Or could be anything else. So first, we need to define some operators that will act as the global spin operators. And it's just the simplest, most direct thing we can do. So we define them like this. So Sx, just Sx on the first one, times the identity on the second, plus the identity on the second, on the first, times Sx on the second. And so on for the other two. So xy, and now the challenge, which is actually very easy, is to show that these new operators satisfy the commutation relations. Z1, identity on the second, plus identity on the first, Z on the second. Okay. And now we need to show that Sx, xy, so these are now the global operators, are Sz, and the same for the other two pairs, right? Okay. So now we prove this. And then we look at the space more carefully. So we need two ingredients that we've seen before, but we'll use now. And so one is that if you have a sum of operators inside the commutator, this is just the sum of the commutators. You see? And the second one is that if you have things acting on a tensor product, and then you have here, for example, C tensor the identity, then this is AC. That's it. I just did the simplest case where we have the identity in the second system. Okay. This, I think we've seen both of this before when we talked about commutators of X and P, right? A long time ago. So now we prove this XY. So now I have to write the whole thing. We have SX on the first, identity in the second, plus identity in the first. Sorry. SX on the second, and I'll put here 1 and 2. XY first. SY on the second. Okay. So we have 4 terms here in this commutator, 2 of which are going to be 0 because they are trivially just acting on different subsystems, right? We also saw this. You can put here ingredient 3. I think you cannot see it on YouTube if I put it there. So 3 is that if things act on different subsystems, then a product is 0. The commutator is 0. Good. So then, okay, let's take the first one. So this is going to be SX1, SY1, tensor the identity on the second. So this would be this and that, right? Plus, now we have this one and this, but they act on different subsystems, so it's 0. Plus, now we have this one here and this. They also act on different subsystems, so it's again 0. And now we have so this thing here and this is non-trivial again, so we have the identity in the first tensor, this commutator in the second, X, XY on the second. Okay. Good. So what's the first one? Well, we know that this first system is a spin system, so this is just IH or SZ1 times the identity plus 0 plus identity tensor SZ2. But this is just AH bar SZ1 identity plus identity, which was our definition of our global SZ. So it checks out, and for the same reason, exactly the same it can do for the other 2 commutators, and we see that they all check out. Okay. So the conclusion is that this HS1, HS2 is a spin system. And the question is, well, what's the global? So if it's a spin system, then we can define the global S square and the global ladder operators. How do they relate to this local ladder operators, local total spin operators? So for example, what are the possible values of S for the global thing? So, and it turns out, we will see one example. I didn't call it, I call it global, it's global. We'll see one example, and for now, again, don't worry about the definition, but we'll do this properly next time. And you can write this as direct sum of Hs, meaning what? That there's different values of S allowed for the global system. Okay, and we will look into the definition of direct sum either in this tutorial or in the next lecture. Okay. How do we find these values? How do we characterize this global space in general? So first, we do a very simple example before we do the generalization. So we look at the simplest case. simplest non-trivial case. So S1 is the same as S2, and they're 1/2. So we have H global, H 1/2, H 1/2. So what are the possible values for M1 and M2? Well, this can only be -1/2 and +1/2, right? They are qubits, essentially. They are electrons. And now we introduce some notation which is very common in particle physics, and it can be a bit confusing. But here it will be good so that we just it's easier to separate to tell apart the local states from the global states. Okay, so I just say the local state when the local M1 or M2 is +1/2. Okay, this I call it up, spin up. So like in a Bloch sphere, the state that corresponds to in qubit notation, normally we call this 0, and it's the one that corresponds to z = 1. So pointing up in the Bloch sphere, and it's the same that corresponds to sz equals plus h power of 2, right? So this is state up. And if you have -1/2, we call it state down. And these all are on subsystem J. And J can be 1 or 2. And this is just going to be easier so that we can look at it and tell if we're talking about the local basis or the global basis. Because for the global basis, we'll have numbers, and for the local basis, we'll just have these arrows. So now let's just write this global Hilbert space. What's the basis for this? So it's H1 tensor H2. And just from we have the local basis up and down for each of them. So for the total one, just definition of the tensor product, we can have up, up, down, down, up, or down, down. And now, now we want to find what are the values of S and M for these states here. So we start with the easiest ones, which are going to be this and this. So what is SZ when applied to this first state? Plus up, up. Well, we just write down what SZ is SZ1, tensor the identity, plus identity, SZ1, SZ2, sorry, applied on this state. Now all this, everything is linear. So on the first one, we have SZ1 applied on up, tensor the identity applied on up, plus the identity applied on up, tensor Z2 applied on up. Yeah. And this is what, well, from this here, this is an eigenstate, so we just get the eigenvalue h bar over 2. So get h bar over 2, because m is 1/2, right? And then up, up, plus, and here we also have h bar over 2 from there. H bar over 2, up, up, right? So it's the same state, h bar over 2 plus h bar over 2, we get h bar up, up. Okay. So from here, we take that m = 1. Okay, don't know much else yet. So what happens now when we apply to the state minus minus? So let me just rewrite again so we have it all in the same place. Up, this was h bar. Up, up. Z minus minus. Well, it's exactly the same. So we get a value, we get minus h bar over 2 from each side. So overall, we get minus h bar. Down, down. And if you apply sz to these other states in the middle, up, down, what we get exactly the same is h bar over 2 minus h bar over 2. Up, down, which is a 0. And sz down, up. Again, you get minus from the first, plus from the second, so you get again 0. So this looks like, okay, here we have m equals 1. Here we have m equals minus 1. And here, it looks like we have two states, which are eigenstates with m equals 0, right? But this would mean that we have something like this, m minus 1, 1 here, and then two states there and 1, right? We just said before that each value of m must have the same number of states. So what's going on here? Well, the solution is that we have two S subspaces, right? So look, we got these two populations together, and now we have a new country. And we thought we only had one language in this country, but it turns out we have two languages in this country. So two values of S. So as it turns out, we'll have subspace A S equals 1 and H S equals 0. So now we have to prove this. Right? And in one of these subspaces, we'll have 3 states, and in the other one, we'll have just 1 state, right? So meaning that there'll be, we'll see how it works. Yeah. So how do we do this? How do we find out? So first, we're going to start on the lowest possible one, and we apply the S minus, and this should give a 0, right? And from there, we find the value of S. So 1, we go from the bottom and then down to find a value of S. So the idea being that this state corresponds to some global M, some global S, and the value of M, we know it's minus 1, right? Okay, so then we say, well, 0 must be equals to S minus S minus 1. But we know that when we apply this operator, we just get H bar, and then here S minus 1. I mean, you can tell already. And then we replace here the M value, minus 1, minus 1, minus 1. And here would be S M minus 2, but we don't worry about this. This state does not exist, right? This state doesn't exist because this coefficient is going to be 0. So from 0 equals to this whole thing, we get that S must be equals to minus 1. I just did this to show that there's a way to do it, but you could also just look at the state and say, look, if this is the bottom, then S must be the same as minus M. Good. So when we found one value of S, now we start at the bottom and we go up to find the next state. So we find all all the values of M for this S. Okay, so let's do this. In fact, we can do it here. No, let's do it here. Sorry, so we apply S plus this state that we found, right? So first, let's just find what the normalization coefficient is going to be. So it's going to be H, and then here is going to end up 1, 0, right? So what is this? It's the value of S plus 1 minus the value of M plus 1. Before I add minus. Yes, that's right. Okay. And now this whole thing here just turns out to be 2. H bar square root of 2, 1, 0. Okay. This was just to find this number square root of 2. Because now what we do is now apply the definition. So let's see. 0, 1. Then is what? Now it's 1 over H bar square root of 2, S plus 1 minus 1. In this stage, we know how to express it in terms of the product basis, right? So this is 1 H bar square root of 2. Now, this state is down, down, right? And this operator S plus, well, we did it before. It's x plus I xy, which if we expand it, it will turn out to be x plus identity plus identity. So this you can compute by yourselves. And what are these states? So locally, these two states are the ones that correspond to as the local spin being 1/2 and the local M being minus 1/2, right? Spin down, like we said before. Okay. So we just do this. So we have 1 over square root of 2 H bar. And now we have the first term is going to be S plus applied on this. Tensor identity is not doing anything. Plus down S plus applied on down. So now what we need to know is this, right? Which you know for the spin case, for the spin 1/2 case, right? So I'll just write it here. S plus when we apply 2 minus, we do this H bar, blah, 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 blah. So H bar, what is S? We said it's 1/2, 1/2 plus 1 minus 1/2 minus 1/2 plus 1. And here you get the next state because you go up the ladder. And this whole thing turns out to be just 1, so we H bar. So we apply that here. Okay. So then we end up with 1 over square root of 2 H bar. And here we got H bar up and the down that was there before plus H bar down up, right? The second H bar comes from here. Okay. So then the H bars cancel out. And this leaves us with an entangled stage, right? So look at this. So we have that 1, 0 is then equal to up, down, plus down, up over square root of 2. So just to remind you, in qubit language, this is 0, 1 plus 1, 0 over square root of 2. And this is an entangled state. We'll talk more about this later. And as a homework, you can check that if you apply now S plus again on this one, you get the top state. So you get the 1, 1. So you can check, can do exactly the same. And check that 1, 1 will turn out to be this. And the way to do it is to just repeat the same procedure. So we apply again the ladder operation and we get there. So what does this leave us with? So now we have one subspace. So the conclusion, we have this subspace. H S equals 1, which is the span. S is 1, and the M can take values of -1, 0, and 1. And what are the states? So we have this -1, which is down, down. Then we have 1, 0, which is not one of this. It's not a product state. It's not one of the states that we saw before. That one would turn out not to be an eigenstate of S squared, but it is instead this thing. So an entangled stage plus down up over square root of 2. And then we have the 1 plus 1, which is up. Okay. So these states are called. The reason why we did all this, I mean, once is that you see in a simple example how it works, then I'll give you the general recipe. The other one is that these states pop up everywhere whenever you have more than one electron. So these are called the triplets because there's 3 of them. It's also called the symmetric subspace. Because if you swap the first and the second electron, you get exactly the same states, right? They don't change. Unlike what will happen for the next subspace. So the other subspace. So now we have 3 states. They are all orthogonal, you can check. But there's still one state left, right? We have 4 states in the basis. So we need 4 states in our new basis to span the whole space. So H S equals 0. This is just 0, 0 and multiples of this. So you can write even span of that to be, if you want to be super precise. And what is the state? So I'll give you the solution now. So it's a state that has eigenvalue 0 for both SZ and S squared. I'll give you the solution, then you'll check in the tutorial that it is, in fact, also an entangled state. Minus. So why couldn't we take one of these states from the product basis before? Why couldn't you take just up, down, or down, up? Because then this state would not be orthogonal to that one. It would also not have this value for S squared. So I'll give you the recipe later for looking for them. But in general, you'll check in the tutorial that this is orthogonal to all these other 3, and that it corresponds to eigenvalue 0 for all these operators that you saw around. So also when you apply the ladder operator on it, you go to 0. This state is called the singlet state. And it's called sometimes also the antisymmetric subspace, okay, which becomes less trivial when you have more than 2 electrons. But the idea here is that if you swap the first and the second, right? If you swap the first and the second here, then you get minus this whole thing. Okay, this question of symmetries, I think, is something you explore in QM2. Okay, so what's the conclusion? that if you have HS1, yeah, sorry, H1/2 tensor H1/2, so 2 electrons. This is equivalent to having 2 subspaces, one with 0. So these are both global spaces, and one with 1. And it looks like this, right? So here you have S, here you have M. So this is your singlet, and then you have the other one. So, okay. So the nice thing here is that you take 2 fermions, and what you end up with is kind of a boson. And this has too many applications to count. And maybe we'll look at one on Thursday. Let's see. Okay. So before we go, I need to tell you the general case, how we deal with this kind of problems when you want to add more spins. So what's the general problem? This is that, well, we have this some product of spins, each of them with a different spin number, and we end up with an H global. And we have the basis for this one. So this whole thing is the span of local basis, right? It's the span of J, of Sj, which is fixed, and then each Sj can have multiple MJs, right? And these are these states here. These are eigenstates of the local operators of S² J and Sz J. Yeah? So this is what we know, what we start with. But then what we want is a characterization of the global thing that is easier. So I want to talk about the global spin operator. Because now if we take 2 electrons together or 2 protons that are somehow glued together through the Stern-Gallagher experiment, you want to see these 3 peaks corresponding to +1, 0, and -1, for example. So in general, what we're doing is that we're looking for a basis here for a global basis of this form S and M. And these are global states, right? In particular, they don't need to be product states. They could be entangled like we saw before, which are eigenstates of the global S² and global Z². So for example, in the previous example, we had 2 bases, right? We had this kind of local basis, which was a product basis, and then we have the global basis. And we saw that the mapping is non-trivial between one and the other. This is what gives us the isomorphism, but we don't care. So in general, this can be much more complicated, right? This was the simplest case. We just had 4 states. So how do we relate the 2 bases in general? So the idea is that we expand the global basis in terms of the other one. So the recipe is that we expand global basis. So we can always expand one basis in terms of the other, right? We just do, well, Sm, this is global, is the same as the identity times Sm. And then I can write this, the identity in terms of all this, these basis elements, right? Like we did before many times. So this would be what sum over all the possible MJs for every J of J, Sj, MJ, and then tensor product again, J, Sj, MJ. And now we still have here the SM. You know, the important thing to take into account here is that this thing here, this is a number. So this whole thing is a number. Because if you look at it, so each of these states lives in the subspace J, in the subsystem J, but you have all of them, so you have global, and this one is global. So then we have an inner product between a global state and another global state. So these are global. And what do they depend on? Well, it turns out that they are fixed. They just depend on the different SJs. So these numbers here are called the, oh, I'll give it a different color even. These are called the Clebsch-Gordon coefficients. And you know, the reaction of most physicists when they hear this is the same reaction as when you mention Brussels sprouts. It's like, meaning what? I'm sure they're healthy. We have to try it once to see how they taste, and the tradition in many places for Christmas, for example. But I mean, we don't have to make them every time. In particular, these Clebsch-Gordon coefficients, these are computed already for most spins. Like if you have 2 or 3 or 4 systems of spins, like between half and 4 or 5, then these coefficients are already computed, right? This doesn't depend on the state or anything. It just depends on which spin systems you choose, right? If I take 2 electrons and the proton, these coefficients are computed somewhere. Someone did it once, we don't have to do it again, so we can look them up in a table. However, we can compute them by hand, and I will just give here the recipe. And I think in the tutorial, you'll do the example for, yeah, I'm not sure if you'll do the example. But I will not ask you in the exam to do this by hand. In general, it's quite horrible to do them. But the recipe is elegant, so we can learn the algorithm. Yeah, so the recipe is step 1. We look at the total dimension of the Hilbert space. So what's the dimension of the total Hilbert space? Well, it's just the product of the dimensions of each of the tensor product factors, right? And this is the product in J of each of them, sorry, SJ, because they have total spin S is SJ plus 1. Yeah. Good. Step 2. And this is actually fun, and you'll do it in the tutorial. So this you can prove is that this Clebsch-Gordon coefficients sorry, SM SM, this Clebsch-Gordon coefficients are 0 unless M is the sum of all the little m's, of all the local m's. So this you'll do in the tutorial. But this means that from these 2, you already know what are all the possible values of m, right? Because you have all the possible values of this, and you just sum them like this, and you get all the possible values of m. So now we know all possible values of m. And they will turn out to correspond to something like, just like you did in the 2-electron case. It's going to turn out to be something like this, where these are the m and S goes there. And most of the time, it will end up having this shape, but we don't know yet this shape, right? But what we know what the, we know the bottom and we know the top, and it should be just one state, right? So this is the corresponding to everyone pointing down, like all of these MJs being the minimum, or all of the MJs being the maximum, right? This should be a unique thing, unique state. So we know it. And for this one, as we saw, we also know what S is. So then we start with, from all the values of M, then we also know all the values of S. Then we start with this S max minus S max. So this is this bottom state here, right? The state there at the bottom. And now we go up the ladder. We just apply S plus, and then we get this state, 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 just like we did before for the 2 electrons when we had spin total spin 1. Okay. So then we get one column, right? So obtain all the states of the form S max M. So now we go look for, let me write a different color. Then we go look for the next one, so the next minimum one. And how do we look for this? Well, this is the top part. For each new S, we need to find the state, the minimum one, right? And how do we get it? This was the same way that we got, that we got this state here, which in this case I didn't tell you, but you'll do in the tutorial. So the idea is to look for one that is, it has to be orthogonal to everything else, and it has to have the right eigenvalues. Okay, so from orthogonality, from, well, if I apply with the S minus on the state, I need to get 0 and so on. Okay. And then from here, go to step 4 again, right? So once I find this state, then again, I apply the S plus and I find all of these states. Okay, then this is done, next one, and I find all of the states, done, next one, and so on. Okay? So if you want, you can even write a program to do this. Okay, so this is it. So just some general notes is that these ladder operators appear everywhere, not just in spin systems, but much more general in condensed matter physics and optics and photonics and whatnot. You always have these ladder operators going up and down. The spin thing is super important. We will see next week. I think on Thursday we'll do examples, but next week we will look at the angular momentum operators, which are very, very similar to the spin operators. So we start from the same commutation relations even. Okay. And yes, so whenever you have particles with the spin properties, so whenever you can find these 3 operators that have these commutation relations, then you can apply this whole formalism and find out lots of properties of this system or materials or so on. So I will try to look for nice examples for us to play with on Thursday. The other case is the harmonic oscillator, which is again very important. So maybe we'll do that one. We'll see. All right, so that's all. I'm happy to take questions. I'm a bit worried no one said anything about typos, but maybe it's because I didn't make any. I doubt it, but let's see. So I'll stop the YouTube stream now.